we are looking at this truss. This constitutes our entire mesh. And now we are going to just take out one element, say element number 4. So we have this element number 4 and it's connected to nodes 2 and node 4. Okay, we are going to take this out and draw its free body diagram. So to do that, uh, we have the global coordinate system, of course, which doesn't change. But for this element, we will take an axial coordinate system, which we'll call the local coordinate system, xl and yl perpendicular to it. Now remember that each node has 2 degrees of freedom. That means it can move in the x or global y directions. So it can move this way or this way. This node can also move this way or this way. So these are the degrees of freedom of this particular node, but degrees of freedom of this particular node, of these two particular nodes. And the truss element has to be endowed with some structural properties. The structural property of a truss element is it cannot bend, it is rigid in bending, but it can only expand or contract along its axis. So along the XL direction, it can become longer or it can become shorter. It cannot do anything else. And the only component of stress that appears in a truss element is sigma LL, which is the stress in this direction. So if I zoom here and take a small element of material out, the only stress that it will be subjected to is sigma LL. And that comes from the fact that the cross-sectional dimensions of the truss element are small compared to the length. And because it's a slender structure, it's a slender element, we can justify that sigma LL will be the only component of stress prevalent in a truss element. So given that fact that sigma LL is the only component of stress and all other components of stress are 0, then the force FL that you have applied and delta L, which is the displacement of node 4 and node 2, the force can be written as sigma LL times the area of the element. So if I look from here, the area of cross section, let's say this is the cross section and its area is A. So sigma LL times A is the total force, and that has to be equal to FL. Sigma LL can be written as E times epsilon. Epsilon is the strain and the strain in the L direction. So this is actually epsilon LL, and epsilon LL can be in the small strain scenario, epsilon LL can be written as L minus L naught. So L minus L is the current length, L naught is the initial length, this is the change in length, and this change in length is written as L minus L naught by a change in length is L minus L naught, that divided by L naught gives you the strain in the LL component of the strain. And then we take these together and call it K, and this is the change in length which we call delta L. Delta L is the change in length due to force F on of this bar, where force FL is in the direction of the local axial the axis along the local axis of the element, which runs along the length of the element. So this is exactly like a spring relation. So FL is equal to K delta L is a spring relation. So you can think of this as a linear spring where K is given by AE by L naught. K is given by AE by L naught being the initial length of this truss element. So this is the constitutive equation. This is the constitutive equation of this particular element. And the constitutive equation is derived from the fact there are two things to note about the constitutive equation. The constitutive equation is derived from the fact that we have endowed it with some structural properties. We have said that it cannot bend, it cannot take any bending, it can only contract or expand. That's the first property. It's a slender element, its cross section is very small. So these two assumptions immediately led us to the conclusion that sigma LL, the stress along the axial direction, is the only stress that can prevail in this element. And then we applied the linear elastic constitutive equation. Sigma LL equal to E epsilon LL is the linear elastic constitutive equation. We applied small strain theory, so epsilon LL to L minus L naught by L naught, epsilon LL is equal to L minus L naught by L naught, is the small strain approximation to the strain epsilon LL. So we use the small strain theory. So here we used Hooke's law. Here we used small strains, and we arrived at a force displacement relation. So whenever our constitutive equation can boil down to a force displacement relation, those are the cases which we will call structural element. So in this case, it's a structural element. We'll later do a beam element, which will also be a structural element, because there also we will deal with moments, displacements, rotations, and forces. Okay. In a solid element, on the other hand, which we will do much later, in solid elements, we'll deal with stresses and strains rather than forces, moments, and displacements and rotations. So in structural elements, typically we deal with forces, moments, displacements, rotations. In particular, for the truss structural element, we deal with only a force along the axial direction and the change in length along the axial direction. So all this follows from a set of assumptions about the constitutive behavior and geometry of this structural element. So that done, so now I know that this is the constitutive equation, F equal to K delta L, where K is AE by L naught, is the constitutive equation of this element when you write them in the XL YL coordinate system, XL running along the axis. So let me then write the free body diagram along the XL-YL direction. So remember, this is node 2 in the global numbering system. This is node 4 in the global numbering system. But now I do a local numbering as well. So the local numbering will be same for every element. Remember, every element in this mesh is connected to two nodes. So the local numbering of the nodes will be 1 and 2 in this case. The global numbering may be something else. It will be something else. But the local numbering will always be 1 and 2. So let's call node 2, global node 2 as local node 1 and global node 4 as local node 2. And then there are 2 degrees of freedom at every node. So this node 2 can move in the XL direction or the YL direction. This also can move in the XL and YL directions, and we call them U2, V2, U1, V1. Remember, the XL, YL directions are actually rotated with respect to the global directions. Right now we are writing we have drawn the free body diagram of this element in the local coordinate system, and we are going to write the force displacement relations in the local coordinate system. But the degrees of freedom of this whole structure have to be finally defined in the global coordinate system. So we will first write it in the local coordinate system because it's easier to write. We know that this truss element can only extend in the XL direction. it can do nothing else, extend or contract in the XL direction. So it will be easier for us to write the force displacement relations. We know the constitutive equations. We've just derived the constitutive equations in this coordinate system. So we can easily see that this should be fx2. This should be fx1. I'll correct it when I upload these notes. So fx2 and fx1. So fx2 will be k times u2 minus u1. This is the delta of delta L. This is the delta L value when this node moves by u2 and this node moves by u1. And similarly, fx1 will be minus of this. So fx1 plus fx2 has to be equal to 0. So here we are using equilibrium. Here we are using equilibrium in a very rudimentary form, where we find that fx2 and fx1 have to be opposite of each other. So fx1 is k times minus u2 plus u1. Okay, so these are fx2 and fx1. Fy1 and Fy2 have to be 0 because there is no resistance to moving this element in the YL direction. You can move it, it just moves like a rigid body. It doesn't resist this motion. So no matter what V1 and V2 you give, Fy1 and Fy2 remain to be equal to 0. Okay, so this is the equilibrium equation of this. So we have now used everything that we had. We had used Hooke's law, we had used the small strain assumption, now we have used equilibrium. So we can now write this down as a matrix equation. How do we do that? So matrix equation between the forces. What are the forces? Forces are fx1, fy1 at node 1, fx2, fy2 at node 2. Remember, these force components are in the local coordinate system, not in the global coordinate system. The global coordinate and local coordinate systems are oriented by some angle with respect to each other. So these are the forces, and these forces can be written as fx1 can be written as k times u2 minus u1. fx2 can be written as k times u1 minus u2. Fy1 is 0, Fy2 is 0. Now this I can now write as a 4 cross 4 matrix. So this is sorry, I have made a mistake. This is fx1 is minus u2 plus u1, and fx2 is plus u. fx2 is plus u2 minus u1. Okay, so now I'm going to write this as a 4 cross 4 matrix with u1, u2, u1, v1, u2, v2. So u1, v1 are the degrees of freedom at node 1, local node 1, u2, v2 are degrees of freedom at local node 2. And then I'll have to write these equations, and these equations would be u1 is multiplied by k, so I'll multiply by k. Fy1 is 0, so 0 here, minus k here, that is for this minus u2, then 0 again. V1 is, so this row should give me 0 because Fy1 is 0, so this is all zeros. And then for this row I should get fx2, and that should be u1 has a coefficient of minus k, this is 0, plus k, 0, then v2, this row gives you fy2, and for that I should get always 0. So now no matter what u1, u2, v1, v2 are, we will get the you'll get the correct set of forces according to the equilibrium equation. So for Fx1, you will get K U1 minus K U2, which is the equilibrium equation for Fx1. For Fy1, no matter what these values are, you will always get 0. For Fx2, you will get K U2 minus U1, which is dictated by equilibrium. For Fy2, no matter what these are, you will always get 0. So this is my local stiffness equation, local element stiffness in local coordinates. So this is in the XLYL, that's why it's local element stiffness in the local coordinates. Now note one thing, that I have ordered the degrees of freedom in a convenient way. I have ordered them as U1 V1, then U2 V2. Similarly, I have ordered the forces as X force at 1, Y force at 1, X force at 2, Y force at 2. So that is the ordering that I have used. If I had changed this ordering, if I had changed this ordering to say fx1, fx2, fy1, fy2, I could have done that. If I had changed this ordering, then this matrix will change. Then this matrix will change and columns and rows will get transposed. You have to finally get these two equilibrium equations out of it. These two equilibrium equations and these two equilibrium equations out of it. So if you change the order, the, the stiffness matrix will change. However, so if you just want to write it in terms of x1 and x2 and u1 and u2, then you can write the equilibrium equations in this form just in terms of fx1 and fx2. But if you want to also include the fact that fy1 and fy2 are always 0, you should better expand this 2 cross 2 matrix, 2 cross 2 stiffness matrix into the 4 cross 4 stiffness matrix, increase the number of degrees of freedom to include u1 v1 u2 v2, and then the forces will include fx1 fy1 fx2 fy2, and you will have the information from the stiffness matrix that fy1 and fy2 are always equal to 0 no matter what these degrees of freedom are. And then we will write it in compactly in matrix notation as F equal to KL times U. U is the vector containing all the degrees of freedom in the local coordinate system. F is the vector containing all the forces in the local coordinate system, and that's why we have the scale, because this is the element stiffness matrix in the local coordinate system. Now if you have if you have n DOF number of degrees of freedom uh, per node, which in this case is equal to 2, and if you have n node number of nodes associated with a particular element, which in this case is also 2, then the size of your stiffness matrix would be n DOF into n node cross n DOF into n node. And in our case, this is 4, this is 4, so my stiffness matrix is 4 cross 4. My number of degrees of freedom are 4, so this is 4 cross 1. 4 cross 4 into 4 cross 1 will give me a 4 cross 1 force. So this is 4 cross 1, this is 4 cross 1, this is 4 cross 4. This 4 cross 4 comes from the number of nodes into the number of degrees of freedom per node per element. Okay, so having derived KL, which is the element stiffness matrix in the local coordinate system, let us now see how we can take it to the global coordinate system. Now, remember, we had the entire mesh. So we have the entire mesh and we have taken this element out. And whatever we wrote is for that element. The local nodes for every element are denoted as 1 and 2 because there are only 2 nodes for this particular element. But the global node numbers are different. One thing that is common, that will always be common between the local elements, elements in the local setting and in the global setting is the degrees of freedom per node is always 2. In the local system, we describe the degrees of freedom, the displacements in this case, uh, in a coordinate system that ran like this for this element. It may run like this for element number 2, and it may run like this for element number 7, and each of these local coordinate systems will have a different orientation with respect to the xy coordinate system. Not only that, because the number of degrees of freedom are 2 in in this mesh for all nodes, uh, when I come to global node number 2, uh, the number of degrees of freedom of this node would be uh, 1, 2 will go for node number 1, then 3, 4 will be for node number 2. So the degrees of freedom, global degrees of freedom, would be 3 and 4 for node number 2. It will be 5 and 6 for node number 3. It will be 7 and 8 for node number 4, and it will be 9 and 10 for node number 5. So because everybody has 2 degrees of freedom per node, then the degree of freedom numbers will be 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10 in for the global node numbers. So when I separate element number 4 out, so when I separate element number 4 out, this is node number 2, and its global degrees of freedom are 3 and 4. And remember, the global degrees of freedom are in the global xyz direction, and we'll call them capital U. So you will have U3 in the global x direction and U4 in the global y direction. Similarly, this is node number 4. It has associated with the degrees of freedom 7 and 8, and therefore this would be U7 and this would be U8. Okay, if I had separated out let's say element number 7, then for element number 7, this node is global node number is 2, and here the global node number is 3. So here you would have U3 and U4, and this is node number 3. You would have U5 and U6. The entire solution would consist of the values of the 10 degrees of freedom that we have in this particular system. So U1 to U10, capital U1 to U10 will have to be solved, out of which U3, U4, U7, U8 are associated with element number 4, whereas U3, U4, U5, U6 are associated with element number 7. Similarly, you can work it out for any element in the system. What you have to remember, that the global degrees of freedom are in the global coordinate system. So for element number 4, which we are now going to look at, for element number 4, the global and the local coordinate systems are not coincident, and therefore the values of U3, U4 are going to be different from the values of U1, V1 at node 2, which had local node number 1, and U3, U4, U3, V3 at node number 4, which had a local node number of 2. So we had derived the force displacement equilibrium relation between U1, V1, U2, V2. This is U2, V2, and this is U2. So we have derived the relation between U1, V1, U2, V2, but we actually need the force displacement relation between capital U3, capital U4, capital U7, capital U8, because that's our global direction. Now this is easy to do. So let this angle be theta. So theta is the angle. This is a two-dimensional problem. XY is your global coordinate system. XLYL is your local coordinate system, and they make an angle theta with respect to each other. And then let us concentrate on this node, which has a global node number of 4 and a local node number of 2. So the local degrees of freedom are U2 and V2, whereas the global ones are U7 and U8. We have worked that out. So now this angle is theta. So we have U2 is equal to U7 cos theta plus U8 sin theta. And we have V2 as minus U7 sin theta plus U8 cos theta. So that just follows, I think. So U capital U2 is U7 cos theta plus U8 sin theta, and V2 is minus U7 sin theta. V2 is minus U7 sin theta plus U8 cos theta. So this is, so minus U7 sin theta is this way, and U8 cos theta is this angle is theta. Okay, so this is the transformation relation between the global degrees of freedom, the global degrees of freedom U7, U8, and the local degrees of freedom U2, V2 at local node number 2. At local node number 1, you would have a similar relation between the global numbers U3, U4 and the local numbers U1, V1, and these are the transformation relations. They're exactly similar. U7 becomes U3, U8 becomes U4, U2 becomes U1, V2 becomes V1. So they're exactly the same relations because this angle also is theta, just like this is. Okay, and theta, how do I determine theta? Remember I told you that the user has to input the coordinates of the nodes, nodal coordinates in the global coordinate system. So these two nodes, their coordinates in the global system x, y are known, and from the coordinates I can easily find out what this angle is. So these are the transformation relations, and now we can write each transformation relation as U2 V2 is equal to cos theta sin theta minus sin theta cos theta U7 U8, and similarly, and let's call this, let's say, transformation matrix T, and similarly I can write U1 V1 equal to T times U3 U4, the same T as here. So now if I want to write the whole thing, U2 V U1 V1 U2 V2, I can write it as a 4 cross 4 matrix where this is cos theta sin theta minus sin theta cos theta of, let's say, so I'm writing, so this is U3 U4, and then cos theta sin theta minus sin theta cos theta of U7 U8. This is 0 0 0 0. So basically this matrix has the form T 0 0 T. This is the partition form of the matrix where T is this unit. Now again, the ordering is important. I know that 1, local degree of freedom 1, is associated with global degree of freedom 2, whose degree of freedom numbers in 3 and 4. So 1, this is local degree of freedom 1, this is global degree of freedom 2, this is local degree of freedom 2, this is global degree of freedom 4. So I have written them in this order so that the local degree of freedom numbers correspond to the global degree of freedom numbers. If we write this in this form, will you get this kind of a transformation matrix, which is partitioned as T00T. If you change this ordering, your matrix also will change, because all that we are writing in through these equations are these relations, these transformation relations. So these transformation relations have to be correct, and if you change the ordering here, this transformation relation will also change. The matrix form of the transformation relation will also change. The transformation relations have to remain the same. So um, that's how you convert it into convert the local displacement vectors into the global displacement vectors. Uh, and since we are uh, doing this for element number 4, we will call this whole matrix here, we'll call it T superscript 4, noting that this is for 4. Remember, theta will be different for different elements. It depends on the end nodal coordinates of the element. So T will be T4, T5, T6, all will be different depending on their respective thetas. So the local force vector, local displacement vector or degree of freedom vector is related to the corresponding global degree of freedom vector for element number 4 by T4. This U4 is the subset of global degrees of freedom associated with uh, element number 4, which are U3, U4, U7, and U8. This is all that I need. Similarly, for the degrees of freedom, we have this relation. Similarly, we should have the same relation for the forces, which are also vectors. So this force is actually my local force vector, which is fx1, fy1, fx2, fy2, which is associated with the global force vector, which will in this case be f3, f4 for the first degree of freedom, and f7, f8 for the second degree of freedom. For this particular problem, all these are 0, but that doesn't matter. We still can write the force in this form. Okay, so the force and the displacement transformations for every node. So if we take all the degrees of freedom of a node, transform it to the global degrees of freedom, force to global force uh, force components, then the relation is the same. It's related by the same transformation matrix, which we have called T4. Now we will convert. We also know the relationship between U and F. We know that KL times U is equal to F. So this relation also we have. Now we know that U is equal to T4 times capital U4, and F is T4 times capital F4. So we can plug it back here. That's what we have done in the next slide. We can plug it back here. So F is equal to KL times U, and in place of U we write T4 times U4. In terms of F, we write T4 times F4, and T4, therefore F4 is equal to T4 inverse into KL times T4 times U4. Okay. However, this transformation matrix has a nice property which makes it orthogonal, and that property is that T4 inverse is same as T4 transpose. This is a known property of rotation matrices. You may be aware of it. So I can replace this inverse by a transpose, and then this is the relation that now relates the forces associated with element 4 to the degrees of freedom associated with element 4, and therefore the matrix that connects these two must be the local stiffness matrix in the global coordinate system. Remember, these are forces in the global coordinate system. These are these degrees of freedom in the global coordinate system. So this must be the stiffness matrix in the global coordinate system, and that turns out to be T4 transpose KL times T4, where KL we have already found as K0 minus K0, 0, 0, 0, 0, minus K0, K0, 0, 0, 0, 0. This is my KL, and if we know theta, we can find these matrices. Multiplying them will give me the local stiffness matrix in the global coordinate system. Now we can do this for every element. For every element, we can go find out its length, find out its material properties, find out its orientation with respect to the global axis, and then we can derive the local stiffness matrix in the global coordinate system in this way. Local stiffness, local element stiffness in global coordinates system. This, on the other hand, was the local stiffness matrix in the local coordinate system. This is the local stiffness matrix in the global coordinate system, because it relates the forces in the global coordinate system to the displacements or degrees of freedom in the global coordinate system. This related the forces in the local coordinate system to the degrees of freedom in the local coordinate system. So this is how you find the elemental stiffness matrix in the global coordinate system. Um, Now you do this for every element, and finally you have to assemble it together to get what is known as the global stiffness matrix in the global coordinate system. How you do that is an important procedure that we will see in the next lecture.